Hello, today we're going to try some past paper questions about the first key area of the waves unit in National 5 Physics. Question number 1. The diagram represents a wave travelling from x to y. The wave travels from x to y in a time of 0.5 seconds. Which row in the table shows the amplitude, wavelength and frequency of this wave? Pause the video and see if you can work out the correct answer. Okay, so firstly, let's consider amplitude. Amplitude is the size of the vibration of the wave. So we can measure that by measuring the distance from the crest to the midpoint of the wave, or from the midpoint of the wave to the trough of the wave. And we can see in the diagram here that the distance from the crest all the way to the trough is 2.6 meters. So the amplitude is going to be half of that distance, which is 1.3 meters. The wavelength is how long the distance is from one wave to the same point on the next wave. Now we can look at this diagram and we can see there are 4 complete waves occurring in a distance of 12 meters. So one wave will be 12 meters divided by 4 waves, which is 3 meters. And finally, frequency is the number of waves produced per second. And as we've just said, there are 4 waves occurring here. And the question tells us that this happens in a time of 0.5 seconds. So we can calculate the frequency as the number of waves divided by time, 4 waves divided by 0.5 seconds, which is 8 hertz. So the answer is amplitude 1.3 meters, wavelength 3 meters, frequency 8 hertz, answer C. Question number 2. A student is studying waves with a period of 80 milliseconds and a wavelength of 4 meters. The frequency of these waves is, again, pause the video and see if you can work out the answer. Okay, so period is the inverse of frequency, or indeed the opposite is also true. Frequency is the inverse of period. The fact that wavelength is mentioned in this question is a red herring. We don't need that at all. To work out the frequency, we can do 1 divided by the period. The period is 80 milliseconds, so 1 divided by 80 times 10 to the power of minus 3, which is 12.5 hertz. Answer C. Question number 3. A student makes the following statements about waves. Firstly, waves transfer energy. Secondly, a wave with a short wavelength diffracts more than a wave with a long wavelength. And thirdly, the amplitude of a wave depends on its wavelength. Which of these statements is or are correct? Pause the video and see if you can figure this out. Okay, so first statement, waves transfer energy. Absolutely true. Secondly, a wave with a short wavelength diffracts more than a wave with a long wavelength. This is false. Short wavelength waves will diffract less than long wavelength waves. And thirdly, the amplitude of a wave depends on its wavelength. Not at all. The amplitude is the size of the vibration of the waves. The wavelength is the distance from one wave to the same point on the next wave. The two things are completely independent of each other. So only answer 1 is correct, so the correct answer is A. Number 4. Which of the following diagrams shows the diffraction of water waves as they pass between 2 walls? Pause the video and consider the options. Okay, so if you said the correct answer was D, you were correct. The reason for that is, as the waves pass by the obstacle, the wavelength of the waves remain the same. So that is why option C and E are both incorrect. We can also see that the wave fronts are, as they pass between the walls, are unaffected. So the flat side of the wavefront remains flat as it passes between the walls. So that is why option B is incorrect. And finally, we can see the bits that drag along the edges of the walls are diffracted. They spread out as they pass around the obstacle. And that is why option A is incorrect. Number 5, a written question. A technician uses pulses of ultrasound, high-frequency sound, to detect imperfections in a sample of steel. The pulses of ultrasound are transmitted into the steel. The speed of the ultrasounds in steel is 5,200 meters per second. Where there are no imperfections, the pulses of ultrasound travel through the steel and are reflected back by the back wall of the steel. Where there are imperfections in the steel, the pulses of ultrasound are reflected by these imperfections. The reflected pulses return through the sample and are detected by the ultrasound receiver. The technician transmits pulses of ultrasound into the steel at positions X, Y, and Z as shown. So, in the diagram we can see at position X, the ultrasound is sent into the steel, reflecting off the back surface of the steel and reflecting back to the transmitter. At position Y, the same thing happens, but at position Y, the sample of steel is thinner. And at position Z, we can see the ultrasound being transmitted into the steel, but instead of hitting the back wall of the steel, it is colliding with an imperfection within the steel sample and reflecting back before it reaches the back wall. The times between the pulses being transmitted and received for positions X and Y are shown in the graph. A part 1. State the time taken between the pulse being transmitted and received at position X. So, what this graph shows us is if the ultrasound is transmitted at time 0, the vertical line tells us when the detector detects that sound being received. The height of that vertical line tells us about the amplitude of the pulse being received. So, what do these two lines represent? Well, the further line represents the pulse being transmitted at position X. We know this because at position X, the steel is thicker, so the sound wave will take longer to return. The other line represents Y. It takes less time to return. The other difference, the height of these vertical lines, is because at position X, the sound wave has to travel further through the steel, and therefore more energy of the sound is absorbed within the steel. So the received wave will have a smaller amplitude. The correct answer is 15 milliseconds, microseconds rather. Calculate the thickness of the steel sample at position X. So we're told at position X, we've just worked out that it takes 15 microseconds for the sound wave to return. How thick is the steel? Pause the video and see if you can figure this out. Okay, we can use the formula distance equals speed times time. We were told earlier in the question that the speed of the ultrasounds was 5,200 meters per second, and we have just said in part 1 that the time taken for the pulse to be received is 15 microseconds. So 5,200 times 15 times 10 to the power of minus 6, which gives us a distance of 0.078 meters. However, we need to remember that this is the distance that the wave travels as it goes into the steel sample, reflects off the back surface, and returns to the detector. So the actual thickness of the steel is only half of this distance. 0.078 divided by 2, which is 0.039 meters. Part B. On the graph on the previous page, draw a line to show the reflected pulse from position Z. Okay, so looking at position Z, we can see here the wave is being reflected from the imperfection in the steel, which is further into the steel than the back wall in position Y, but not as far as position X. Therefore, the sound wave will travel further, so will take longer to be received than the wave from position Y, but less time than from position X. It will also have absorbed, or less energy will have been absorbed than wave X, but more energy have been absorbed than wave Y. So we want a vertical line like this on our graph, which is smaller than the line from wave Y and taller than wave X, and positioned in between the two. Next, part C. The ultrasound pulses have a period of 4 microseconds. Show that the frequency of the ultrasound pulse is 2.5 times 10 to the power 5 hertz. Pause the video and try and work this out. So, this is a show that question. In a show that question, you must always begin with a formula that is on the formula sheet. Here, I'm going to start with this one. Period equals 1 over frequency. That's the definition of period, the inverse of frequency. The opposite is also true though. Frequency is the inverse of period. So frequency equals 1 over capital T. In this case, the period is 4 microseconds. So 1 divided by 4 times 10 to the power of minus 6, which is equal to 2.5 times 10 to the power of 5 hertz, which is what the answer was asking for. Part 2. Calculate the wavelength of the ultrasound pulses in the steel sample. Pause the video again and see if you can work this out. Okay, so we've been told previously in the question that the speed of the ultrasound waves was 5,200 meters per second, and we just showed in the previous part of the question that the frequency was known as well. So we can use our V equals F lambda formula. Start by writing the formula from the formula sheet, V equals F times lambda. Speed is 5,200, as we were told earlier in the question. Frequency, 2.5 times 10 to the power 5 hertz, as we showed in the previous question. Lambda is the wavelength that we're trying to calculate. So, lambda is 5,200 divided by 2.5 times 10 to the power 5, which is 0.021 meters. Part D. The technician replaces the steel sample with a brass sample. The brass sample has the same thickness as the steel sample at position X. The technician transmits pulses of ultrasound into the brass at position P as shown. The time between the ultrasound pulse being transmitted and received at position P is greater than the time recorded at position X in the steel sample. State whether the speed of ultrasound in brass is less than, equal to, or greater than the speed of ultrasound in steel. You must justify your answer. So, pause the video and have a little think about this. Okay, the 2 points that you need to make here. First of all, the speed of sound in brass is less than that in steel. And we can see this because it tells us that the thickness of the brass is the same as the thickness of the steel, but the time taken for the pulse to be received is longer. Therefore, we can see this as it takes longer for the pulse to travel the same distance in brass than in steel. That takes us to the end of this question. I hope you found this helpful. Perhaps you should now move on to the second key area of the waves unit, the electromagnetic spectrum. I'll talk to you again soon.